Welcome friends. In the previous lecture we talked about resistance and the power generated in resistances. Okay. The consumption of energy, etc. etc. Today we are going to talk about the source of getting that power, and we are going to talk about the topic therefore runs like this: cells, EMF, internal resistance and combination of cells. Here, okay, I'll come back to this EMF. First of all, as I told you in the beginning of this current electricity, that there are cells which are shown like this, and if they can vary, then we put a sign of variation here. Okay. It's also called, a cell is also called a source of EMF. Okay. They are also called these days power packs or power supplies, because mostly we are using electronic power supplies, but we'll deal in what are the cells. Well, I have just shown here that the load resistor, where we want to push a current in and out of it. Current means rate of change of charge through the resistor, and here is an arrangement which is basically an electrolyte in it, a chemical, and a chemical reaction takes place, so that this point P, the positive point, and N, the negative point, they have the potentials at the point A and B respectively. Okay. This Vp will be equal to Va, is called V plus, and this Vn is equal to Vb, we call it minus V minus. So the potential over here is positive and the potential over here is said to be negative. Okay. Now, so the potential difference between P and N, this turns out to be equal to V plus minus V minus, which is equal to V plus V minus. Okay. And this is what we call and represent by the letter, it's like E, and this is the EMF. And the EMF of the cell is greater than 0. Okay. So we have in circuits, we have a representation of an ideal cell, and that you can only understand if I make a representation of practical cell, plus minus source, this is the ideal cell, in series with a resistance small r. This small r could be put here also. Okay. And sometime back, this small r used to be put here in some of the British texts, just to show that this resistance is offered by the electrolyte. Okay. Anyway, so that doesn't matter whether you put this R here or put this R here and put this R over here, it doesn't matter that. In the case of the ideal cell, this R is considered as equal to 0. Okay? That is, there is no internal consumption of power while the cell is functioning, while the cell is working. Okay. So let me see the very, very simple arrangement where I have shown that there is a cell and there is the consumer, the resistor, which is the load resistor. Okay. Now, the current flows outside the cell from positive terminal through this connect, through the R, and through this connect back to the negative terminal. Okay. It's a very simple thing. I will tell you, just now demonstrate to you why it is there. Okay. But let me introduce to you what is the natural flow of current when a cell arrangement is there, whether it is an ideal cell or a practical cell. Okay, let's talk about a practical cell, where there is an internal resistance. There will be an internal resistance, howsoever small. The natural flow of current outside the cell is from positive to negative. Okay? From positive to negative. But inside, and it's very natural because the current has to flow continually, therefore inside it has to flow from the negative terminal to the positive terminal. Okay? So inside, negative to positive. Okay? That's something I'll tell you again. But before that, I will demonstrate to you about the why there is an internal resistance. So look here, friends. Suppose I have this ball and this is on a chute or on an incline. I put it on the incline and it goes and falls there, comes back over here. So what I do if I want to continue this process, I will pick up the ball again and put it back on the track. And again, and again, and again, and again. What will happen to me? I'll get tired. Because I have to pick that ball up. So what does the cell do? One more thing, it's very important. Historically, current is a flow of positive charges. The explanations that we'll give, the current is a flow of positive charges from higher potential to lower potential. We will not talk in terms of electrons. Okay? We will be far from the truth. No. So, the current is a flow of positive charges in this circuit. Right? Now suppose a positive charge traveling all the way comes to the cell, to the negative terminal of the cell. So what does the cell do? It raises the positive charge from a low level to a high level, from a negative potential to a positive potential. It does work. it spends energy. Okay, that energy is provided by the chemical energy of the electrolyte and the charge. Once it is there, then again it goes like this. Then pushed up, then again it goes like this. And again and again. And this current I is maintained. It is the steady current. Okay. Now we were talking about that inside a cell, in a natural flow of current, it flows from the negative to the positive inside. And against its nature, if in a circuit, if it flows from positive to negative, then it is forced. It is forced by some other cell which has a larger E value, which I am now going to take the name that was provided to it historically long back, and it was called electromotive force. And they were the days when even electricity was not taught in schools and colleges. But people used to work on that and talk about that. This is about 1700 and odd things, when it was developing into a vast science. Now, here I show you a two-terminal network, and a cell is a two-terminal network. I'm just showing it 1 and 1 dash, and between the terminals 1 and 1 dash, the voltage is called, the potential difference is called terminal voltage. And this terminal voltage is equal to what I call EMF. I was saying electromotive force. We used to write it fully electromotive force, and we also used to write it as capital E dot capital M dot capital F in our school days. Not very long back, around 50 years back, EMF used to be written like this. Then people are always getting wiser, argumentative, and they said that there is no force. It is only an energy which is being transferred. So some people suggested that let us write it EME, electromotive energy. But there were others who said, no, we have been writing it for 200 years as EMF, electromotive force, so let's do that. But finally we agreed that we will write it with small letters E, M and F together. Okay? Don't call it M, but call it EMF for historical reasons. That history is very dear to us. Like, historically, the current is defined as the flow of positive charges. Okay, there was an attempt made that the flow of electrons should be otherwise, and people rejected it, that we are not going to distort the history. Anyway, so friends, now what is the situation I told you? That this will be done. So you must have seen the cells or the battery of cars. If battery of the car has been lying just like that for a long time, no use, then we say that the battery has discharged. And we take that battery to a workshop where all that they do is a very simple thing. Your discharge battery, like this, is connected. This is plus, this is minus, and this is connected through a resistor, which is the dissipating thing, to a charged battery. What is a charged battery? A charged battery has either the EMF more than E1. This has to be there, a little more than E. Okay. So the current which is pushed by this battery is more than the current which is pushed by this battery. And the net current is like this. It goes like this. And now look here. In this battery, the current flows through the battery, inside of the battery, from negative terminal to positive terminal. But in this cell, in this battery, it flows from the positive terminal to the negative terminal. And what is the purpose of this continual flow of current is that, suppose at the time that it was discharged, the internal resistance of this cell was R1. Okay? And after quite some time, this internal resistance, instead of R1, it becomes R prime, which is less than R. So therefore, the charging of the battery takes place and the current flows until the current flow has to stop. Because the EMF, the potential difference over here and the potential difference over here, they become equal. So that is why when, even if sometimes a battery of a car is discharged and your car is functional, and then there are two leads and you have to connect. Then how do we connect? We connect positive to positive, negative to negative. Okay? And then, because they are connected, the two batteries there, so you can make the other car start, keep it started for some time when its resistance becomes minimal. Okay. Well, we have batteries, small charge batteries, a positive and a negative. Normally 1.5 volts. Okay. So you know, and I will tell you when we talk the combination of cells, that if we put one and the other, and then this 1.5 plus 1.5 is 3. Okay. 3 plus another combination, 3 plus 3 is 6. Okay. And 6 plus 6 is 12. Okay. So 6 plus 6 is 12. And suppose there is an appliance like a car which works on a 12 volt battery. Will it be possible for us to put those cells and make a potential difference, make a V11 dash, the terminal voltage, okay, to be 12 volts? Will that start? The answer is no. Because the internal resistance of the total battery situation is much larger as compared to that of a car battery. Okay. So that will not function, that will not work. We'll talk more about it. So let us redraw the simplest possible circuit that I drew for you with a cell of EMF E and internal resistance R, and there is a load, okay, the one that could be any kind of a thing, appliance, which is consuming the energy, okay, and we have the lovely formula V is equal to Ri, and now let us travel to find as to what is the potential drop, okay, while we are traveling through the path of the current from A to B and from B to A. So the circuit is complete. The path of the flow of the charge is complete. This basically, we are talking about the law of conservation of charge. Okay. So from here to here, this positive, this negative, and the current is flowing. So the drop of potential over here will be equal to R into I. This which I have shown over here is small r. From here to here, the drop of potential will be R into I, and then there is no drop of potential. Instead, there is a rise of potential from B to A, and therefore I'll write it as minus E, or E is the EMF. Okay. So we get I is equal to E upon the EMF upon R plus R. Okay. And if we talk about the best value of R, then the best value of R is 0, or as close to 0 as possible. Which means, less the value of R, the better the cell, because then we have more current for a fixed value of capital R. Now, if I do away with this R, that is, I connect it with a straight wire, then the maximum current that can be drawn, I max, will be equal to capital E upon small r. And this is what is called shorting a battery from outside with the help of a wire. And whenever the delivery boy comes and he wants to show you that the battery is fully charged, they will take a wire and put it there just momentarily, and there will be chat 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 and sparking, and he will say, look here, now your battery is ton. Okay, isn't the best to say? So that provides the rating, how we rate one battery from another battery, etc. Okay. Now let me take up the combi, just introduce the combi of the cells. And in a simple case, we are just taking two sources of EMF, where the negative of this is connected to the positive of this, etc., etc. Okay. And now, if we are not drawing any, current can be drawn, of course, when we take this like this and put a resistance here, then a current is going to flow. I am not going to talk about that aspect. I am just traveling from here to here and just looking at, in the condition that no current is being drawn, then what is the value of the effective value of the EMF? So you can see that plus minus, plus E1, plus minus, plus E2, and between these 2 points, the terminals of this combination, we have the total EMF and the combination of these two cells, which I am showing here. And here also we will say that if I travel in the equivalent case from here to here, then this is equal to E. No current is being drawn from the cells. So the net value of the EMF is equal to E1 plus E2. And the net value of internal resistance is equal to R1 plus R, with an if, with a but, with a but, with a but. And the but is like this. Suppose this terminal is positive, okay, then what happens? Then between this and this, the EMF will be equal to E1 minus E2. But the resistance will be, because the resistance of an ideal cell is taken as always equal to 0. So this will be 0 plus a small r1 plus 0 plus a small r2, and that is r1 plus r2. So this will survive, okay, but the value of the net EMF, and if you put the two cells, by the way, by chance, if both the EMFs are the same, okay, then what we will get is, you cannot draw under any case any current from that cell, because E will equal to E1 minus E1 or E2 minus E2, and turn out to be equal to 0. So we have to think about that. There is another way. I'm just introducing that to you, and I want you to be prepared in the next, to attend the next lecture. That's the ideal way, the parallel combination. And in the parallel combination also, if you are drawing currents, etc., etc., it all depends. Oh, it's not E1, this must be E2, okay. So we have two cells. So what will happen if you travel like that? So there will be a value of an E, which will be the terminal voltage that we will obtain here. In case both the cells are similar, okay, E1R1 and E1R1, then of course the net EMF over here is the simplest possible case that will obtain at these two terminals will be E1. And when we estimate, we calculate the value of R1, the equivalent R, then this equivalent R will turn out to be equal to two resistances R1 and R2 in parallel. So the value will be equal to R1, R2 upon R1 plus R2, the product upon R1. This and this, and more so about these, I am going to talk to you, okay, maybe it is little different from what is normally done in books, okay, in the next lecture. So please wait for the next lecture, and that may be quite interesting. Okay, thank you very much. See you again.